Yeah, so in the last class, actually, we tried understanding how we can sample and quantize an image. Uh, then we also saw what do we mean by uh, high contrast image, what is the meaning of dynamic range, and we also saw how we can calculate the number of bits used to represent a digital image. And an extension of this, we solved a problem on actually calculating the time required to transmit 500 frames. We made a small mistake there. I think probably Swati, I think she identified what was that mistake. Uh, that is why actually I have sent you the corrected version of the problem. Hope you would have seen what is a mistake we did. Uh, so all of you should have noticed the only, in fact, the calculation of number of bits was correct, but when we are calculating the time required, I think this is where we went wrong because the problem actually it is 3 megabits per second. I just took 1 megabit per second in this case, and I just took 1 gigabit per second in the second case. Actually, this figure we didn't notice during problem. So it is actually 30 gigabits per second. So it is given as 30G and 3 megabits. So that is a change, I think. So it is this calculation was correct, what we did in the last class. While calculating the time to transmit, we should have taken 3 mega, I took 1 mega. So we were getting something like 5242 and it is 1747. Okay. So is this problem clear to you? Can anybody respond? Hello?
Yes, sir.
Okay, okay. So with this, now let us just move on and we will continue with our discussions. Okay, now the question is, uh, so we talked about spatial resolution, and it is the smallest, uh, in fact, discernible detail in an image. That means how many bits are used to represent the data. And of course, it is also in terms of what is known as dots per inch. This is a measure that is used actually. So many dots per inch. Each dot is a pixel there. So per inch, what is the number of pixels? That is how it is measured. And in satellite images, normally the resolution is talked in terms of actually the area that is covered by each pixel. What I mean is, suppose if I have a satellite camera which is of 1 meter resolution, the meaning of this 1 meter is 1 meter on the earth, 1 square meter. That means 1 meter along x direction, 1 meter along y direction will be actually the okay 1 pixel on the image. So every 1 meter by 1 meter on the earth will be mapped as 1 pixel. So if I say 1 meter resolution of a satellite camera, so whatever that is visible by the camera within 1 meter by 1 meter is converted into 1 pixel. So that is a resolution now. I think now the satellite camera resolution has also gone up to almost zero point 0.6 meter resolution. So that is what I meant by resolution. Now the question is, what happens if I change the spatial resolution of the image? For example, if you look at this image, this is a 1024 cross 1024 image, and it is actually an 8-bit image. Now, if I uh, downsample this to 512 by 512 or 256 by 256 and etc., 32 by 32, what you notice here is the size of the image is reducing. In fact, the why it is reducing, because on the computer screen every pixel will be mapped to some area. So if it is 32 by 32, definitely the area that is mapped to this image will be less. That's why it is looking small. So if you want to really see what would be the effect of spatial resolution, a variation in the spatial resolution, you should actually show all of them to the same scale. Okay. So that's what is done in the next image here. So what is done here is, this is a 1024 cross 1024 image. 512 cross 512 is shown with the same area, because you want to see what would be the effect. And this is 256 by 256. This is 128 by 128, 64, 32 cross 32. So now only I can see what would be the effect if the resolution is less. So I hope you notice here, particularly on the edge of these petals of the uh, uh, flower. So you could see an effect here, which we call it as checkerboard effect. Okay, please notice. So this is a very important concept. So it's called checkerboard effect because it looks like checkerboard of your chess game. So as you can see, so this effect is called checkerboard. So what I notice is, if I try to reduce the spatial resolution of an image, then I notice what is known as checkerboard effect. So it is better if I have higher resolution, this checkerboard effect is decreased. For example, 32 cross 32, it is very clearly visible. 64 cross 64, I hope you can notice here. I don't know on your mobile camera how does it look, but you can notice here there is a checkerboard effect. Here also there is a checkerboard effect, but not much noticeable. And of course, here you don't see it at all in these cases. So at least a minimum of 256 cross 256 would be a good resolution to start off. So this is 256 cross 256. So this is a good resolution to notice that there is no checkerboard effect. Okay. So this is okay. Let me just try to demonstrate this by using MATLAB. Okay, so I'll just go to a demo. I hope you can notice what I am doing here is, please notice, is the MATLAB window visible?
Yes, sir.
Hello? Yes. Okay. So I am just reading an image. It is a child image and showing it. And there is a command in MATLAB called IM resize. As the name itself says, it is resizing the image. So image X is resized to 50%. This value is 0.5. So 50%. So if the original image is say 1024 cross 1024, what you get is 512 cross 512 after resizing, and I am showing it. And here I am resizing it to 25%. That means 1000. It will be 256 cross 256, and I am showing it. Okay. Then what I am doing is, I just to show it to the same size, I am just resizing it by 2, resizing the next one by 4. Okay. So because I hope you remember what you need to do is, if you want to see the resolution, effect of change in the resolution, I should see them in the same size. So what I am doing here in MATLAB command is downsample it and then resize it by just using some resize command. So let me just show you this demo and notice what is happening. I think I need to change the, okay, yeah, yeah. So this is the child image. I'll just demonstrate it, what happens. So you can see this is the original image, and this is after resizing it to, I think I'll just probably run the first portion first so that it would be easy for you to understand that. Okay. So notice this is resized by 4, and this image is resized by 4, and this is the original image. This is the second image. Okay. So if I just show it at a higher, bigger scale, I hope you can notice probably the checkerboard effect here, the checkerboard effect at the edges. And I think it's more clear in the next image. Let me just show it. So hope you can see that checkerboard effect. Okay, is this visible on your screen also?
Yes, sir.
Okay, fine. So this is the effect of change in the resolution. So I repeat, when I change the spatial resolution and when I go to the lower spatial resolution, we start seeing what is known as checkerboard effect, because we need to represent the data at a bigger scale. So what happens is you need to resize it by using some interpolation technique, and this interpolation technique definitely introduces the effect. Okay. Now the next question is, so here we talked about spatial resolution. Okay. That means how many pixels I am using to represent the image. And lower the number of pixels I use to represent the image, you start seeing the checkerboard effect. Now let us see what happens when I change the gray level resolution. I hope you remember when we did sampling and quantization, the number of quantization levels is decided again by the number of bits used to represent the data. So if I use 8-bit, then the number of quantization levels will be 256. If I use say 2 bits, the number of quantization levels is only 4. So now the question is which quantization level or which how many bits I should use to represent the image. Okay. So gray level resolution, as you know, it is the smallest okay change in gray level that I can notice. Now what you observe here is um, this is a 452 cross the 324 image. I am now talking about the spatial resolution now. Now this is an 8-bit image. That means I use 256 gray levels to represent this. Now if the same image is shown at say 128 gray levels, that means I'll not use 256 gray levels, I'll use 128 gray levels. How does it look? And here I use 64 gray levels, and in this case I am using 32 gray levels, and here you are using 16 gray levels, 8 gray levels here, and here 4 gray levels, 2 gray levels. For example, notice here you only see black and white here, no other values are there. So there is a black, that means one gray level, there is white, which is second gray level. Now here you observe there is black, hope you can see that, there is white, hope you can see that, and in between you have two more gray levels, one is this and other is this. Hope you can notice that there are 4 gray levels. Okay, if you want I can zoom it just to see. So observe here, this is one gray level, that is this black, white is second gray level, this is third one, and this is fourth one. So there are 4 gray levels in this. So 4 gray levels means I am using 2 bits to represent 0001, sorry, 0001 1011. Okay, so hope you can notice the change here. Okay, now observe carefully, particularly in this. You can observe here, there is a contour that has formed here. There is a second, okay. So you can see that there is an effect. In fact, it's very visibly seen here. This is one gray level shade. This is a second gray level shade, and this is a third gray level shade. So this formation, which was not noticed in the original image, see that is not there. In the original image, it is not there, but when I reduce the number of bits to represent the data, you start seeing this contouring effect, and this is called as false contouring. Why it is called false contouring? Because it's actually not there. Because I have less number of bits to represent the data, you have started seeing some false contouring effect on the image. Okay, so this is exactly what I want to in fact convey. When I have insufficient number of intensity levels in okay, particularly in smooth areas, you start seeing this false contouring effect, and it is expected because you have less number of gray levels. Here I could differentiate them because I have more number of gray levels. Here all these things are assigned one gray level. All these are assigned one gray level. So obviously you start seeing this false contouring effect. Let me just demonstrate this by using MATLAB window. So again, I am reading an image, and I am actually dividing each gray level by 8. Okay. So, 256 divided by 8, it will be 32. So I'll have 32 gray levels in this image. I am dividing by 16 here. Okay, so 256 divided by 16. Okay, 16 gray levels you will have. I am dividing by 32. So you can have 8 gray levels here. And I am dividing it by 64. You will have 4 gray levels here. So let me just demonstrate this for you. Okay, so I think it's very visible. This was the original image, and this is when I used 32 gray levels. Okay, you already started seeing some false contouring effect, 32 gray levels, and this I think is 16 gray levels. So you can see the contouring effect is more visible here, or even on the hand, you can see. Okay, this portion you have some contours. Then I think this is some 8 gray levels. I have 32. Yeah, 8 gray levels. And the last one is 4 gray levels. Okay, you can very clearly, in fact, count the gray levels. So there is a white gray level, there is a black gray level, there is a gray shade here. So 1, 2, 3, and 4. So I have 4 gray levels. Now you can see that contouring effect. Particularly, it's more visible here. Very nicely visible. Okay. So the moral of this MATLAB demo is whenever I reduce the gray level or the number of bits used to represent the image, that means the quantization levels is decreased, we start seeing what is known as false contouring effect. Okay. Particularly this is visible in smooth areas, not at the edges. In smooth areas it is visible, which was not there in the original image. Okay. Is there any doubt? I have demonstrated it using MATLAB also. Any doubt before I go to the next topic? Somebody should respond. See, I want you to please speak.
No doubts. No doubts.
Okay, okay, fine. Okay, and also see, I think a lot of things are being discussed. I am just assuming that you are noting down these points on a notebook because it's always better, because I cannot see these slides will be shared, don't worry. And of course, the video I'm also sharing. But my point is sometimes it is better you note down the points, so because particularly the keywords, which are they are important when you are answering questions. Okay. Now the next question is, we have discussed about what happens when the spatial resolution decreases, what happens when the gray level resolution decreases. Okay. Now what is good? Which spatial resolution is good? Which gray level resolution is good? Okay. A rough rule of thumb, it may not be true always, but a rough rule of thumb is, as I told you, 256 cross 256 resolution is okay. You saw it there. For example, this was 256 cross 256. I didn't notice any checkerboard effect here. Okay, and when it comes to the gray level resolution, you could see that the false contouring effect is not visible here, whereas as you go to 32, it is already visible, as you can see. So 64 gray levels and 256 class 256 is a good okay in fact resolution, but still we use 8-bit resolution because 64 it is 2 to the power of 6. Okay, so when I want to process it, I hope you remember when I was just talking about the resolution, particularly the gray level resolution, usually it will be power of 2, 2 to the power of k, and this k normally will be 8, which would be 8 or 16. So usually, even though 64 gray levels is more than enough for me, but we still use 8-bit for representation because processing 8-bit at a time is is actually easy in hardware, because most of our hardware will have 8-bit or 16-bit processors or 32-bit or 64-bit, which is again a power of 2. That is why even though 64 gravels is okay, we use 8 bits. Okay. But it is enough. I have 64 gray levels for representation because uh, Beyond this, there won't be any false contouring effect that is visible. Now, just to demonstrate for which image, which resolution I should take, this person Huan, he has actually conducted a subjective test. What we meant by subjective test is, I think you should understand this. Subjective test means you just perform the operation and show it to people and ask them what do they okay notice. Okay, that means the opinion of the people will be taken, and based on the opinion of people, you will come to a conclusion. That is why it is called subjective. That means it depends on the individual's perspective view of that particular data. Now, what he has done is he has taken three images. One is this Lena image, second one is cameraman, third one is a crowd image. What you should notice is crowd image has got large amount of details. You could see that lot of people, person wearing specs here and different color, and they are, so that means finer, lot of okay details are visible here. When it comes to cameraman, it has some mid-level data. What I mean, there is a strong edge here. You can see that the color is suddenly going to black. Okay, there is a strong edge here. See the color of this in fact tripod stand is black, whereas here it is different. So there is a strong okay edge here, and in fact in the background you also see some weak edges. I hope you can notice that there is a building here. Okay, and there is a transition here, which means there are edges here which are weak. We call them as weak edges because the change is very less. There are strong edges here. Now this is called a mid-level detail image, and this is a low-level detail image. So you don't see much variations except some variations in the eyelid region here. And this is actually a mirror. So this border of this mirror, or maybe it is maybe the okay, transition. So this is a low-level detail image. This is a mid-level detail image, and this is a high-level detail image. Now what this person did is he took these three images, change the spatial resolution and the gray level resolution of each of them, and he has shown it to the people and he has taken their opinion, and this opinion is plotted as a curve, and these curves are called iso preference curves. Okay, iso preference curves, because the preference, when it becomes same, and that preference is actually plotted. So notice here on the x-axis, it is the spatial resolution variation. He has actually taken square images. So both the rows and columns is same. So on the x-axis, he is plotting uh, in fact, the spatial resolution. On the y-axis, the number of bits used to represent. That means the gray level resolution. So at 32, at 64, cross 64, at 128 cross 128, at 256 cross 256, at 4-bit resolution, at 5-bit resolution, etc. He has shown it to people, and this is a part of the result he is trying to show. Okay, fine. So what you notice here is when it comes to the face image, that is the Lena image. Okay, when it comes to the face image, uh, at 128 by 128 size spatial resolution, this is the preference of the people. That means they expected okay, they gave a same preference at about 5 or 6-bit resolution, but uh, when the spatial resolution changes, you could see that the opinion as is actually in fact for the lower resolution. Now, when it comes to cameraman, which is a mid-level image, so it is somewhere like this, and the opinion is passing this or following this curve when the number of bits used, sorry, number of pixels used for representation is here. But when it comes to the crowd image, as you notice, uh, the preference is whether I show it at 4-bit or 5-bit, the preference is same. So what this gives me is a crowd image shown at 4-bit resolution, shown at 5-bit resolution, the opinion of people has not changed much. Okay. So that's what it means. Images with large amount of details, few gray levels are needed. That means when the opinion is same, what I mean, I don't see any change when it is shown at 6-bit and when it is shown at 4-bit. So why should I use 6-bit for resolution? I'll use 4-bit for resolution. I hope you understood. Okay. So this is how he actually proved that if it is a high level image, lower gray level, large amount of details are there, lower gray levels is enough. That's what he concluded. You don't need to go for higher resolution. But if it is a mid level or maybe a low level image, then probably higher bit resolution is giving a better opinion when compared to lower bit resolution. Okay. So I hope you understood in fact, the objective of this particular test done by Yuan. In fact, it was way back in 1965. Okay, so I think this actually is what we would like to cover as a part of okay, the basics. That means what is resolution, what is spatial resolution, what is gray level resolution, what is the effect when it is changed, and which is good for me. Now, some simple operations on such type of images. All of you, I think, for example, let me just do that. Uh, okay, so what I'm trying to do is I'm actually zooming. If you carefully observe, I'm just trying to zoom. Okay, and I'm just trying to zoom in. Okay, so this is zooming in. In fact, without knowing what is really happening inside, all of you have done this whenever you have downloaded some images. If the size is too much, you have reduced it. If the size is very less, you have increased it. I think this now we are trying to understand under the heading of what is known as image zooming and shrinking. Okay. Uh, so zooming is actually, in fact, it is viewed as oversampling, and shrinking means it is undersampling. So zooming means you are trying to add more pixels to the image. Shrinking means you are trying to remove pixels. That means you are undersampling. You are reducing the number of pixels for representation. And normally this is done for digital images. Okay. In fact, what you see on the computer screen is a digital image. So zooming and shrinking, now they are applied to digital images. Okay. Now let me just try to demonstrate or explain this by using probably I'll just write on the board, which is better. I think video is not required now. Let me go to the okay. I'll explain it for you to understand 2D. Now let us assume that I have maybe a digital data. Is the OneNote page visible?
Yes, sir.
So let us assume that I have some data like this. There are 3 samples. Let me take this value as 2 and this value as 3 and this value as 1. That means I have a signal x of n which is having 2, 3 and 1 as the values. Okay. Now I have 3 samples. Let us assume that I want 4 samples. Okay. I want a new signal x of n which should be calculated or which should be determined. That means I need to have 4 samples now. So what do we do? Carefully observe what I am trying to do. So I'll just start with the first sample. Now what I want is actually this width is 2. I hope you can understand. This is 2 units. 1 unit here and 1 unit here. So it is 2 units. So in the remaining 2 units, I need to have 3 samples. Okay. So in 2 units, 2 unit distance, I need 3 samples. So what should I do? I should place every sample at 2 by 3 location. Okay, so in fact this is 1 and this is 2, so you need to put one sample at 2 by 3. Okay, so this width is 2 by 3. So the next sample will be at another 2 by 3. So 2 by 3 plus 2 by 3, that is 4 by 3, somewhere here. Okay, so the next sample will be at another 2 by 3. So 2 plus 4 is 6 by 3, which is at 2. Okay, I hope you noticed what I have done. What I am showing on black color is actually the new samples. Okay, let me just now show the original samples here. So there is a original sample here which is 2. What I am showing in red color is the original samples 3 and 1 here. Okay, so I need to calculate these new samples. Of course, first sample I'll retain it as it is. I need to now calculate the second sample. I need to now calculate the third sample, and of course the fourth sample will be this itself. Okay, so now this new sample has to be calculated. This is a new sample which I need to calculate. And how you do it? Can anybody tell me? How I determine this new sample? Can anybody? What method we use? What technique we use? Hello, anybody? Am I audible?
So to find a slope.
Okay. To slope, see, okay, I'll explain it like this. See, I know this value, I know this value, I need to calculate this value. Now, can you tell me? I think in mathematics, you should have done this. Okay, okay, I think clue is not clear to you. So actually, I'll use what is known as an interpolation technique. I think this you should know. Okay, use
Yes,
interpolation
sir.
to calculate this new sample. Okay, so there are many interpolation techniques. One of them is called nearest neighborhood interpolation. Nearest neighborhood. As the name itself says, the new sample, just copy the nearest neighbor of this new sample, because you already know the original samples. Whichever is nearest to the new sample, you just copy that. Okay, now if I do that, if I use okay, nearest neighborhood interpolation, in fact, okay, I think you should tell me. 2 is your original first sample. So what will be the next sample? Can you just tell me what will be this? I have given you the distance, so you should tell me. This new value, you know the neighbors. Which are the two neighbors for this particular sample? Okay, let me call this as A, and this I'll call it as B. Can somebody tell me which is closer to A? Which are the two neighbors for A?
So 2 and 3, sir.
2 and 3, right? So which is closer to A?
Yes, sir.
3, correct, because you know the distance is 2 by 3 here, so which means this distance will be 1 by 3. Therefore 3 is closer, so I'll just copy 3 to the next sample. Okay, what will be B? I think other than Shivam, somebody should respond. It is not good keeping quiet. Please interact.
1, sir.
Who is it?
Yes, yes.
Pardon?
Yes, yes.
Yes, yes, good. Okay, how do you say it is 1?
Because it's nearest to 1. 1 because 2 by, no, sorry, 4 by 3 from 8,
Pardon, see, wait a minute. What are the two neighbors to B? Tell me.
3 and 1.
3 and 1. So what is the distance of B from 3?
4 by 3 minus 1 by 3.
No. See, this distance is not 4 by 3. I think I have marked it wrongly. This distance is 4 by 3. This distance is actually 4 by 3. Now tell me, from here to here it is 4 by 3.
1/3.
Yeah, correct. So this distance is actually from 1, this is 1 by 3, so this will be 2 by 3. Correct. So which neighbor is closer to B?
3.
3 is closer to B. So you copy 3. And of course, the next sample will be 1 because that was the original sample. Okay. This is your new x dash of n, which is having 4 samples. Your x of n was having 3 samples. Okay. So I started off with 2, 3, 1, and I have just added one more sample and I got 4 samples now. Okay. Please notice what I have done. I had given you the input and I had told you what is the output number of samples. I wanted 4 samples. So first I calculated at what distance I should keep each of this new sample. Then I looked into nearest neighborhood and then calculated what are the new values. Is this procedure clear to you? This is for 1D. We have to do it for 2 dimension. We will do it later. This is for 1 dimension. Is this point clear? Any doubt?
No doubt.
Okay. Okay. So the second method is bilinear interpolation. Bilinear interpolation. Because nearest neighborhood has got a problem. Carefully observe here, both neighboring pixels are getting same pixel value. This is going to introduce an effect, which I'll show you later, which is your checkerboard effect. So bilinear interpolation is better. And how this is done is, I'll demonstrate it by just using only 2 samples. Let us assume that I have a sample A here, I have another sample B here, and assume that I need to calculate a new value x here. This distance you can take it as say some delta x, and obviously this distance will be 1 minus delta x because the complete total distance is delta, 1. This is one sample, this is second sample, that is the known samples, this is the unknown sample. Okay, this is the situation. Now the value of x, okay, using bilinear interpolation is the following. It is a into 1 minus delta x plus b into delta x. This is the formula you are going to use. In the previous case, you took nearest neighborhood. That means the importance was given to only the neighbor which is closer to it. But you never cared about the other neighbor. It is farther, but its effect will be definitely there. You know that. But here you can see that you are giving importance to A, that is the one neighbor, important to be the other neighbor. Both are given importance. And that importance is calculated by this scale factor. This is the scale factor, delta x and 1 minus delta x. So carefully observe now. Suppose if your delta x is equal to 0. Okay, what should be the new value x? Can somebody tell me? Delta x is 0 means this value should be lying on this point. So x has to be equal to a. Obvious, right? So when delta x is 0, x will be equal to a. And when delta x is equal to 1, x has to be equal to b. So what you notice is as the value of x, as the new sample goes closer to b, its importance will increase or its significance will increase when compared to a. But both are given the weightage. This is bilinear interpolation. Okay, now with this, I want you to give me the values for the same example that we took. This sample is 1. Okay, I'll just show it using red color. So this value is 2, this value is 3, and the next value is 1. So I want to calculate this sample anyway is already calculated. This is a new value, this is a new value, and this is a third value. Okay, so this value is 2, we have already calculated. In fact, it is 2. Now, what would be this value by using bilinear interpolation? Let me give you these distances. What is this value? Can somebody tell me? I think it's there. It is 2 by 3.
2 by 3.
Correct. So since this is 2 by 3, this value will be 1 by 3. And this we saw, this value is 1 by 3 and this value is 2 by 3. So let me call this as A and this as B. Now what is the value of A? A and B are to be calculated. What is A? Formula. Of course, here I am using A, B only, so don't get confused. So what is the formula? How do I apply this? Can somebody tell me?
8 by 3.
No, I don't want final answer. First, give me the steps because that is important. Give me the steps.
2 plus 2 by 3.
How? 2 into what? A into 1 minus delta x. A is this now. Okay, if you have confusion, let me call this as A dash and B dash because I think A, B I am using it for. Okay, this is A and this will be B for it. So now tell me, 2 into 1 minus delta x. What is delta x for this?
2 by 3.
Correct. So 2 into 1 minus 2 by 3 plus B. B is 3 here. 3 into delta x. Delta x is 2 by 3. Okay, so this is A dash. 1 minus 2 by 3 is 1 by 3. So it is 2 by 3 plus 6 by 3 as somebody told. Who was it? 8 by 3 is correct. A
Yeah.
dash is 8 by 3. Okay. So similarly, can somebody tell me what is B dash? For B dash, what is A and B?
3 and 1.
Yeah, correct. This is 3, this is 1. So this will be A and this will be B for B dash. Okay, so what is B dash now?
7 by 3.
No, final answer. I want the steps because please understand the steps. 3 into 1 minus
1 by 3.
1 by 3 plus 1 into 1 by 3. So this is 6 by 3 plus 1 by 3, which is 7 by 3. So the values are 2, 8 by 3 is how much by calculator? 2.67. P dash 7 by 3. So 7 divided by 3, 2.33, 1. These are the values. Okay. This is by bilinear interpolation and by nearest neighborhood it is 2331. Okay, I'll write that in different color. This is by bilinear interpolation. By nearest neighborhood it is 2331. Now notice here there is a smooth change from 2 to 2.67, 2.6 to 2.33 and 1. Okay, so actually this will is a smoother data, whereas here there is a change from 2 to 3, it remains same, and there is a change from 3 to 1. So this has got some sudden variations. So nearest neighborhood is not good. I'll show this on an image later, but this is what is the concept. Okay, let me just repeat what we did. We had some data and you want to zoom it for a higher dimension. So the first point we did is first located the new positions, correct? I located the new point. Then I calculated the new values by using either an interpolation, a nearest neighborhood interpolation or bilinear interpolation. Okay, so let me now go back. Now it is easy for you to understand. Okay, now carefully see the slides. So zooming requires two steps. One is the creation of new pixel locations. Correct? Is this correct? Because that's what we did in one dimension. First, you should create the new positions, then assign the gray level to these new positions. So you have to now calculate the gray level to do these new positions. Now, how this is assigned? It is assigned either by using nearest neighborhood interpolation or by using bilinear interpolation. Okay. This is for zooming. Of course, same effect can be done for image shrinking by a factor of integer. Okay. Um, of course, you can also use the procedure. Of course, if the factor is maybe an integer factor, then I can just use row column deletion. What do I mean by that? Let me just like demonstrate it here. Assume that I have a signal x of n, which is 1, 2, 3, 4. And let us assume that I want x dash of n, which has got only two samples. It is an integer value. Okay, so the best thing is take alternate samples. I hope you remember downsampling operation. X dash of n, this is your signals and systems, equal to x of 2n. Hope you remember this. You have done signals and systems. Okay, so I'll take the alternate samples. I'll take 1 and I'll take 3. And I'll discard 2 and 4. That's exactly what it says. By a factor of integer shrinking, if I have to do, just do by row column deletion. This is done for 1D case. We will do it for 2D case maybe in the next class. It's already time today. Okay, so this is exactly what it means by image zooming and shrinking. Okay, so uh, since I need some more time to explain this, I would probably not start the next topic because it needs some explanation how we can calculate these values, and we need to do a problem on this. So just to wind up, image, we will take it in the next class. Yeah, I think some of you are actually answering me through chat window, but once I share and I go to the complete slideshow mode, I'm not unable to see this chat that you are doing. I think Sumuk and Suresh have given the answers by linear interpolation. So answer is correct, but unfortunately I have not noticed it because I was on full, uh, in fact, screen mode. Anyway, it's okay. Good that you are responding. So we will meet in the next class. That's on Wednesday, and we will discuss how we can do this zooming and shrinking in the next class. Today afternoon at 4 o'clock, B section students should join through this link only. I would like to see the progress of your lab. So join through this link only. Okay. So let us now stop. Thank you.